Okay, good morning. This is the lecture 18 mechanical vibrations, and uh, it is going to be a long presentation. Part of it has to do with the fact that there's a lot of math in it, and this is not the advanced math. It's elementary math. It's the stuff that people did in their second year differential equations course. But I don't want to throw the formulas at you. It is just that as much as I want to show you how they're derived at, and then we do a whole bunch of examples. Now, we're going to be dealing with the damped forced harmonic vibration. Okay, we started it on Tuesday, but it's a situation when you have a mass spring damper system. Uh, and then we have a right-hand side, which is a force, but this is not an arbitrary force, it's a harmonic force, okay? Uh, some of this derivation I did, some of these presentation I did on Tuesday towards the last half an hour, but it's going to be a quick review for those who have already seen it. So we have the situations spelled out here, no big deal. We just write down the mother of all equation, which comes from the statement that the sum of all the external forces equal to mass times acceleration. So external forces are the damping force, spring force, and the applied force, harmonic force. And of course, when you write it, equal to mass times acceleration, and clean it up, take the stuff which involve x to one side and the load on the other side. This is the equation that you get. Now, anything that we do in this presentation right now, it applies to the other three cases that we looked at. In other words, undamped free vibration, damped free vibration, and undamped forced harmonic vibration. Okay, so this will take care of those three cases. However, it would have been foolish for me to go and start here and say that, oh, it covers those things that we didn't do. Okay, so let's move on. Another way of writing this thing, a very classical way of writing this thing, is to reduce the three parameters here, m, c, and k of the system, into two parameters, and the two parameters being the zeta damping ratio and the natural frequency. And to do that, divide by m, so you get a coefficient. You get a coefficient 1 here, and you get c over m. C over m, you can write it down. It's going to be this expression. And k over m obviously is the square of the natural frequency, omega and square. And then this quantity f0, little f0, is simply the big F0 divided by m. Okay, so basically here's the situation. This is what we're dealing with. Now, okay, it says the differential equation. In differential equation, it is known that the forced response of a damped system is also a harmonic under a harmonic response, under a harmonic force, is also harmonic of the same frequency. This is a matter that if the right hand side is a harmonic force with a frequency omega, such as sine omega t, such as cosine omega t, etc., the the steady state response is also going to have the particular solution is also going to have the same frequency, okay? But there is a phase shift involved and in this situation, okay? So the moral of the story is that what I just said, what is written up here, is that the particular solution has the same frequency, it's harmonic, same frequency, but there is a phase shift because of the presence of the damping. If there was no damping that we did on Tuesday, this theta will be 0, of course. And there is there's an amplitude that we have to find. We have to find x and theta. Okay. Now, in order to develop this, it is easier, or at least Inman has decided that it's easier, and that is true, that if you write a trig identity to take the cosine of the difference of these two angles as the product of the cosine plus product of the sine. So it's going to be cos omega t sine theta, cos omega t cos theta plus sine omega t sine theta. Okay. So the combination of big X times sine of omega t we call A sub S. This is for convenience. That's the pathway that the Inman takes. In other words, this is a solution, and so is this. This is just by massaging this expression using trig identity. And now notice that when you write it like that, this X, big X simply becomes square root of this plus square root of that. If you don't believe it, square these up, add them up. You're going to get x squared. Take the square root, you're going to get this. And then you divide these two, you're going to get tangent of theta equal to bs over as, and theta is equal to tan inverse. Okay? So the thing is that we want to get the coefficient as and bs. I mean, look, here we had the our challenge was to find big X and theta, but we massaged it like that so that we're down to AS and BS. Get AS and BS. Okay, so you know what XP looks like. Differentiate it twice, plug it in there, clean it up. In other words, put all the things that are multiplied by cosine together, put all the things that are multiplied by sine together, you get this. The only way this can be true is if the first bracket is 0 and the second bracket is 0. And you have two equations and two unknowns. Remember the unknowns were AS and BS? And if you find AS and BS, you have your big X and theta. There we are. This is nothing advanced, just two equations, two unknowns. Work it out, you get this. And of course, big X was the square root of AS squared plus BS squared. After some algebra, elementary algebra, you get big X equal to this. And theta, remember, tangent of theta was the ratio of BS over AS. So BS over AS is written, cleaned up, because they have the same denominator, and you get that. So we beat it. In other words, we found the solution to the damped harmonic problem. Okay? All right. Now, the question is, okay, what if we are given initial conditions, initial x naught and initial velocity v naught? How do we solve the problem? Well, the solution is made of, you know that the solution is made of two parts. First, set this thing equal to 0 and solve. And that is the content of lecture 4. And we did it. Then the particular solution that we just found now. So the moral of the story is that this is the solution of damped free vibration, which means the right hand side equal to 0. Go to the previous lectures, lecture 4 maybe, and then this is what we just got now. All right. Now, if you have the patience, you set in this expression t equal to 0. This is going to be x naught. You differentiate it. You set t equal to 0. X dot at t equal to 0. That is v naught. So if you have the patience of finding a and phi out of the two equations that I mentioned, x naught equal to dot dot dot, v naught equal to dot dot dot, you're going to get your a and b. A and phi. Okay, because we already know what x is, big X is. We already know what big theta is. That's written for you down here, right here. Big X is this, theta is that. But when you solve these two equations to find a and phi, they will have x naught and v naught in it, right there, x naught and v naught, and they will have this stuff in it, okay? Things involving big X and cosine of theta, because, for example, in this expression, when you set t equal to 0, this becomes big X cosine of theta. So it's going to be there. The moral of the story is that this A and this phi come from the initial condition. In their expression, you will have x naught and v naught, obviously, and you will have things which are inherited by that steady state response right there, big X and theta. It's going to be there. Big X and theta are not unknowns, they're right here. All right, this is coming from Inman's window 2.3 in his book. In his book, he has summary of the stuff, and he calls it windows. All right. Now, what I just did for you is fine. There is no problem. But remember, this was one way of writing that initial solution to the homogeneous equation, right there. See that? We could have written it like this, or we could have written it as, for example, a1 e to the minus xi omega nt sine of omega d cosine of phi. So the moral story is there's going to be a constant times exponential times sine of omega d plus another constant exponential cosine of omega d. Okay, so this was another way of writing this. This A1 and A2 will absorb that phi in it. Remember the cosine of phi and sine of phi that's going to come? They're going to absorb. So another way of doing this is to say, okay, I know these, plug it in there, get A1 and A2, differentiate it, plug in t equal to 0, get another equation involving A1 and A2, and I'm going to solve for A1 and A2 this way, instead of that, solving for big A and the phase angle phi. We're saying that we're going to do it, we can do it like that. Algebra, nothing complicated. So this A1 is going to come out to be that expression. Notice that in it we have x naught, all right? And A2 is going to be that expression. In it we're going to have x, we're going to have x naught, right? And we have a v naught, you can see that. And this expression, although you can write it like that, there's nothing wrong with it. It's just that you can also write it as big X cos omega t cos theta plus big X sine omega t sine theta. So it's written as cos omega t sine omega t and cleaned up. Yeah? So there we are. Either like this, horrible, or like that, well, a little bit more civilized. Move on. Okay. So let's do some examples. It says compute the constants of integration big A and phi, remember from previous slide, and compare the values of big A and phi for the unforced formulas. Now, what does that mean? Remember, when we did damped free vibration, but 4 lectures ago, we had an expression for big A and phi, which involved x naught and v naught. Today, we did damped forced vibration, and also in it, we have something called A and something called phi. So the purpose of this problem is use the right expression. In other words, the stuff that we did today. Don't go and use the big A and phi that you saw in the lecture, I don't know, a week and a half ago, 2 weeks ago. Okay? Don't use that. The whole purpose is, what if we did both of them? Would they be the same? The answer is absolutely not. And how different are they? So obviously you have some information here given to you. You're told that omega n is 10 rad per second. The forcing frequency is 5 rad per second. You're given zeta, so 0.01, which is 1% damping. And then F naught is given to you, M is given. Initial position is 0.05 meter, and initial velocity is 0. So what we're saying is that we move the mass to some location, release it from rest, and at that same time that it vibrates, there's a harmonic force acting on it with this frequency. So we just write down what we know. This is the stuff that we know. All right? Eventually we're going to find big A and phi, right? So first of all, the down frequency is needed. It's going to be this, omega n, root of 1 minus zeta squared. We need little f naught, which is big F naught over m. So 1,000 over 100, that's 10. Go to the formula for big X, and theta. Because notice that big X pops up when we try to find A and phi. It will, okay? So big X is equal to, just plug in this stuff in there, 0.133. And theta, just plug in there, you get 0.013 radian. Now, the solution was this. The solution to a damped harmonic response subject to initial condition looks like that, okay? So what do we know? We found X, we found theta, we have to find A and phi, right? Okay, we just plug it in, and we get A and phi can be directly calculated from this information that's given. Okay, so let me go ahead. You just plug in the expression for phi. Remember we did it 10 minutes ago? Plug in the expression for A. In order to do that, we had to know what X was and what theta was, and we just did it in the previous slide. Just write it down. Okay, so now we go to the stuff that we did 2 weeks ago. There was no forcing involved, but there were formulas. You can see these formulas, this formula from 2 weeks ago does not involve big X and theta, because there was no big X and theta. There was no right-hand side. The right-hand side was 0. So if we accidentally went and plugged in the stuff that we know in that expression, you're going to get 1.5561, and A is going to be 0.05, which are different. You can see that. This is 1.55, this is 1.56. It could be more dramatic. This is negative 0.083, this is 0.05. They have nothing to do with the conclusion. You see the constant integration are affected by that forcing term, by that big X and theta. They're affected, you can see that. And you have to be careful. Don't use these, because that can dramatically change the problem. Now, this is important to notice that the amplitude of the transient right here, this is the amplitude of the transient, this is the amplitude of the transient here, this is the amplitude of the transient here. The phase didn't matter that much, but see, there's a dramatic change in the amplitude of the transient response, okay? And if that is important, if transient response is important, you have to make sure that's included and the correct thing is used, not this. This is not the correct thing. All right. Now, very often, I should say, it is the case that at least in some mechanical engineering applications, the effect of the transient is ignored. For example, and only the second part, which is big X cosine of omega t minus theta. That first one involving the dyne response of the transient may not be of interest in certain mechanical engineering applications, such as, for example, you have a motor sitting on a table, it because of its unbalance, because of rotation, puts a vertical dynamic force, harmonic force on the table. It goes up, 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 up and down, up and down, up and down. Of course, initially there is some damping because of the things that the table has, or etc. But that dies down. So in the situation like that, you're interested in the steady state response. Just throw away the transient one. But in some applications, it cannot be done. For example, if you look at the earthquake, for example, earthquake application, it's the transient that kills. The steady state essentially is going to be not critical. So anyway, uh, all right, so it says usually devices are designed and analyzed based on steady state response, but the transient should always be checked to make sure that it's reasonable to ignore it. Okay, all right. Now I want to remind you that the magnitude of big X and theta, uh, the magnitude of X and the phase theta of the steady state response as a function of the driving frequency is given in the, this is a review in this form. This is the steady state response. This is the magnitude. This is the phase, and we have the expression for them right here. Big X, once again, is given like that, and theta is given like so. Now, for the next few minutes, what we're going to do is rewrite this. In other words, this is fine. There's nothing wrong with it. However, it turns out you get more insight into the whole problem or the solution response of the system by, instead of writing things in terms of omega n and omega separately, write it in the form of the frequency ratio. So what I'm going to do, I'm going to get rid of omega n. You're not going to see it, but in return, you're going to see something that is R, and that's what we're going to do for the next the rest of the lecture. Okay, so what I told you is that although the expression for big X and theta are fine as it is given in those long fractions, it is more you get more insight if you rewrite those so that you don't see omega and omega n by themselves separately. You see the ratio of omega omega over omega n, which is called the frequency ratio. So let's go there. So what I'm going to do is that expression for big X, okay, big X, and I'm going to divide the right-hand side of it by the top and the bottom by omega n. Okay, so this is what's going to happen. Please go back to the expression for big X. Go back to the expression for big X. You will see that if you take the right-hand side and divide the top and the bottom by omega n, or omega n squared if you want, or omega n, this combination, xk over f naught, which is incidentally, it is this, because look, remember f naught, if you look at little f naught was big F naught over k, right? Sorry, big F naught over m. And if you write big F naught over m and clean it up, you get xk over f naught. The moral of the story is this. Instead of saying x equal to dot, 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 we are writing big X times k over f naught. We look at this combination, which has no dimension. This has no dimension, because look at it like this. If you take the k at the bottom, f naught over k is a static deflection. It's a deflection. And x is a deflection, no dimension. Okay, so this combination is there. There is no separate omega and omega n in it, because we already made the division top and the bottom. So we get omega over omega n ratio. This is called the frequency ratio. And the same thing with theta. If you go back to the expression for theta that I had there, notice that if you rewrite it in terms of R, you get that. The moral story is that X, big X, is in terms of R. Theta, of course, R and zeta, right? R and zeta. Big X is a function of R and zeta. And theta is a function of R and zeta. So if you plot these things, you get the non-dimensional amplitude. See that? This is not X anymore. This is X divided by static deflection, which is F naught over K. And all I'm saying is that, look, this combination, you can plot it for R, and depending on what the value of the damping is, you get these curves. And this theta, you can plot it as a function of R, depending on what the value of zeta is. So, for example, look at it like this. When damping is very light, when there is no damping actually, when there is no damping, you get 1 over square root of 1 minus R squared squared, or 1 over 1 minus R squared. If you take absolute value, no damping, this is gone, you get 1 over 1 minus R squared. And what do you know? When R is equal to 1, when omega is equal to omega n, big X goes to infinity because the denominator becomes 0. So there it is. If we are looking at the no damping situation, the curve starts like that. When it reaches the value of R, it shoots to infinity. And on this side, it shoots to infinity. But when there is a damping present, light damping, it doesn't go to infinity. You can see it brings it down. Real life, it doesn't go to infinity. It brings it down. High amplitude, because this is non-dimensional X basically. Large non-dimensional X, okay, but not infinity. All right. And there are some observations here that we're going to make also. Notice, for example, when there is no damping, actually when there's no damping, it looks like this. No damping means that no phase difference. Shoots at R equal to 1, shoots all the way to, goes through pi over 2 and shoots all the way to pi, and it goes like this. So for a non-damping situation, it's like this. Flat, vertical, flat. As there is a damping, a light damping, this flat becomes curved. It doesn't shoot all the way instantaneously. It slowly, as R increases, approaches that behavior. Okay? This tells you a few things. For example, a few more things, actually. When R is a small values of R, very small values of R, that means omega is very small compared to omega n. Omega is very small. That means essentially we have a load that is applied that has a very small frequency, extremely large period. So basically it's a static problem. That's why this height, for example, for R close to 0 is height of 1. Because at the end of the day, here we have a static problem. We can see equal to 1. What does that mean? Equal to 1. Xk over F naught equal to 1. It says X is equal to F naught over K. Magnitude divided by displacement, by stiffness. It doesn't even see that cosine harmonic term. So for very small frequency ratios, we have a static problem. For extremely large frequency ratios, that means omega goes very, very, very fast, much faster than omega n. Actually, the mass does not even have time to move. That's why you can see that the amplitude is very small. Very large frequency, the mass doesn't have to move, doesn't have time to move a lot, and therefore amplitude is small. Very small frequency ratios, basically you have a static problem. Close to or equal to 1, we have a gigantic rise in the amplitude, which means resonance. Doesn't go to infinity because of damping, but it does have resonance. Something else that you see here, although phase in general difficult to visualize, like amplitude, but it tells you that uh, at resonance, when R is equal to 1, regardless of the damping, that phase theta, that phase angle theta, is always pi over 2. You can see that. For R equal to 1, regardless of what the amplitude is, that value of theta, irrespective of what damping is equal to pi over 2. All right. Okay, so we're going to do an example next. So by the way, this combination, which I told you that this is a non-dimensional entity, some books, they call it dynamic magnification factor. Okay. I don't think Inman puts a lot of emphasis on that notation, but anyway, this has no dimension. It tells you in a dynamic problem by how much the static deflection is increased. Okay, remember, F big F naught over K, if I divide this thing by K, F naught over K is a static deflection. No cosine stuff. So this tells you, this magnification factor, dynamic magnification factor tells you by how much do we have to multiply the value of static deflection to get the dynamic amplitude. Okay, think about it. So this is drawn here. Let's make some observation. I think these are useful, and it's repeating what I told you. As the driving force approaches undamped natural frequency right here, the magnitude approaches a maximum value. The maximum value, not quite at that R equal to 1, but you can see that there is a peak here. Okay, and but that peak does not exist if damping is too high. You can see that for high values of damping ratio, there is no peak. Okay, so that's the statement. As the driving frequency approaches the undamped natural frequency as R equal to 1, the phase shift crosses the 90. You can see that. We already mentioned this. And that's irrespective of the value of, when R is equal to 1, that's irrespective of the value of the damping. As omega approaches 0, which means that R approaches 0, because remember, R is omega over omega n. If R approaches 0, omega approaches 0, essentially we have a static problem. Then we can see that, static deflection. And finally, as R gets bigger and bigger and bigger, we go to the right, which means omega gets bigger and bigger and bigger compared to omega n. The mass does not even have time to move, so the amplitude is very small, and in fact, in the limit, it goes to 0. Now, a couple of other comments before we do an example is that these peak values can actually be worked out. It's just some algebra, you can work it out, because you can write down the expression for m. This is the expression for m. This thing is the m function. This is the m function. These are all m functions for different values of zeta. To get the maximum, you differentiate it patiently, differentiate big M, that magnification factor. Set it equal to 0, get the value of R, get the peak. So if you do that, you're going to come up with these conclusions. In other words, the location where these peaks occur is close to 1, close to where we expect the undamped things to happen. Okay. But if you want the exact value, it's right here. And this actual height, the actual height is given there. Incidentally, look at this. When zeta is small, when damping is very small, basically R is 1. So essentially as if we had a, no damping at all, kind of. And the height, the actual height, notice that when when zeta is 0, no damping, there is a 0 here in the denominator, and this goes to infinity as we expect, because undamped the undamped situation shoots to infinity, does not peak at a certain value. Oh yeah, and there is no peak. You can work it out. There is no peak if the value of the damping ratio is less than 0.707. Okay. As far as the phase goes, is one thing you have to remember. One, obviously you can calculate it, and usually when you calculate theta, the phase, you're going to put it in your calculator, and the calculator will spit out an angle between pi over 2 and minus pi over 2. Okay, because you know the tangent of theta, right? So you have to do the inverse tangent to get theta. When you do inverse tangent in calculator, it spits out a number between minus pi over 2 or pi over 2. You have to make sure that you adjust it so that the phase theta is always between 0 and pi. That's a must. Otherwise, you're going to get the wrong phase. As simple as that. Okay. So you see, the phase shift is calculated from the arctangent function, which must be computed to come out between 0 and pi. 0 and pi. Your calculator spits out uh, negative values between pi over 2 and minus pi over 2. You have to adjust it so that it comes in the right quadrant. Okay, just keep that in mind. And then we're going to do an example in a few minutes. Okay, the first example that I'm going to be doing is this viscous or damped force oscillation. And of course, the forcing is harmonic here, as we have been doing it since the Tuesday, and we're going to be with it for another maybe week or so. The information that's given, the mass, the stiffness, and the damping values, and the driving frequency is 32 rad per second. And this, the value that's given to you in terms of little f naught is 10. Remember, little f naught is big F naught over m. So if m happens to be this number, you can work out what the amplitude of the force is here. But anyway, we are assuming that little f naught is this number. So that's what I'm going to be using. It says obtain the expression for the steady state response. Now, remember, the expression for steady state response is little x of t equal to big X, okay, big X times cosine of omega t minus theta. Okay, now, I will not, so we have to find big X and we have to find theta, but here I will only find big X for you, and I will leave out the theta for another example. Okay, so first we find the natural frequency, square root of k over m, okay, which is 132, which tells you that actually the frequency, the driving frequency is the same as the natural frequency. Therefore, we're kind of at resonance. If we're close where r is equal to 1, r is equal to omega over omega n. Remember that? And we'll use that later. Now, we need the C critical here, which is 2 square root of km, to find the zeta, to find the value of zeta, because remember, the value of zeta is going to pop up in big X, okay? So we need the C critical, which is given here, 2 square root of km, plug in, you get this number. And if you take a ratio of C over C critical, you get your zeta value right there, zeta value. And now we're going to go to that expression for the magnitude, the absolute value of the xp, which is the magnitude, which is the big X basically. This is the amplitude. This is the amplitude of xp of t. So we have a formula for it. It can be done like that, or it can be done using the R value, the massage formula. The massage formula says big X is equal to F naught over K divided by that. But you can also write F naught over K, remember, as little F naught over omega n squared. Little F naught was given to us, omega n squared, omega n we calculated. We have the value of R is 1, and zeta, we just worked it out, so we can plug it in there, okay? get 0.034. I can find the theta too, but that's really not what I'm going to do, because I want to show you what happens if the driving frequency is a little bit smaller. For example, instead of 132 rad per second, it's 100, let's say 125 rad per second. If you do this, if you do exactly the same thing with R, with omega equal to this, which means R is going to be 125 over 132, you're going to get big X equal to 0.005, 10 times smaller than that. Okay, so it says a slight change in the driving frequency near resonance can dramatically affect the amplitude, and you can see that by an order of magnitude. Okay, good. The second problem that we're going to do is this piston, and this piston is 100-pound piston. It's for maybe a naval application or something like that. It's not a car, definitely. And it's supported by stiffness, by a spring of certain stiffness. Okay, think about it like that. Now you can think about this spring being the, for example, the connecting rod, that kind of a thing. Okay, and there is damping here because of the motion and things like that. These are all models. We are told what to take. Okay, based on some other modeling and maybe experiments, etc. So we have the mass, then we have the weight of the piston, we have the stiffness of the spring, and the damping coefficient for that damper. And the pressure that's applied to it is fluctuating. You can see that, fluctuating pressure. So it is harmonic load, you can see that. And the surface area of this piston is 80 square inches. Now, we need the surface area because all the stuff that we're doing in this vibration course are dealing with the force, okay, not the pressure. You have to multiply by area to get the force. All right, it says determine the steady state displacement as a function of time and the maximum force transmitted to the base. Essentially, it says what is xp of t? Remember, it's big X times cosine of omega t minus theta. We have to find big X and we have to find theta. Incidentally, this is your omega. This is the driving frequency, 30 radians per second. Okay? So let's go ahead and get the stuff that we want. First of all, the mass of the block we need. So the weight divided by G. Remember, the G, if units are consistent, is okay, so the mass is going to be weight of it divided by G. G is 32.2. And this actually is not correct. It should be slugs. Okay, so this is a mistake. This is not slinch. This is going to be pound divided by 32.2 feet per second squared. This is slugs. Incorrect. All right, let's move on. So we have the square root of k over m. Now remember, because we are using feet as our unit, then this 200 pound per inch should be corrected to be in terms of pound per foot. So we have to multiply this thing by 12. So that's okay. Rad per second. And zeta, the damping coefficient is C over C critical. So we put the stuff in here. We know everything that we need. We find the zeta. And we move on. Frequency ratio is omega over omega n. All right. And this is the value of R. Now go to the formula, which gives you the amplitude. You can write it like this. This equal to that, or this equal to this. By the way, this was called the magnification factor for information. So we have everything, and we're going to calculate big X. Okay, you can plug in omega n, you can plug in F naught, or big F naught, either way. And there's the expression for the uh, angle, phase angle. All right, so it looks like we're going to use that version of it. That's because F naught is given directly in terms of that pressure. Of course, you have to multiply it by the area. Pressure, amplitude of the pressure was 0.625. You multiply it by 80 square inches and then divided by K, so everything is consistent here. You just plug it in, you got the zeta and R, and you plug it in, and you get your displacement in feet. Okay, everything is converted to feet. All right, and we move on. Okay, so by the way, remember that this 0.625 was PS pound per square inches. If you multiply it by 80 square inches, you get pounds. So that is correct unit. So theta, just plug it in. And now remember, the problem is that the angle theta must be between 0 and pi. The calculator spits out for you, if you tried it, the calculator will spit out for you an angle which is in the first or fourth quadrant. So you have to add pi to it in order to get it between 0 and pi. Okay, just think about this. So that is the correct value of theta, not what the calculator spits out. Okay, if you put this in your calculator, this is what's going to come out. But theta must be between 0 and pi, so you add a pi to put it in the appropriate quadrant. Now, the second part, it says determine the steady state displacement. We did that as a function of time, and the maximum force transmitted to the base. Okay. So here's the solution. Here's the whole shebang. Okay. So what is transmitted to the base? Well, there is a force of the spring, which is kx or kxp, plus the force of the damper, which is cx dot p. So we literally have to go and put the k here, multiply it by that, differentiate this thing, multiply it by c, and it's done there. So based on this expression, here is x, here is x dot. You're going to get a negative sign because of that cosine, right? And then the maximum value of this, if you don't believe it, square root of kx quantity squared plus c omega x squared. Please make sure that you understand why that is the case. Okay, the easiest way to see that is again to factor out the square root of kx squared plus c omega x squared, and then you get, it becomes kind of easier in that sense. So if you factor this out, you're going to get this guy divided by that you factored out, plus this guy divided by the thing that you factored out, and there we are. I mean, that's where it's coming from. Now, if you plug in numbers, you're going to get, if you don't believe me, take all the values that you know k, you know x, you know omega, you know theta, just plot it, and you see that this is going to be the maximum value. Okay. Now, I'm going to do it a different way. For example, we know that this is the transmitted force, right? The transmitted force, we know it's this. We know that. We know it's this. We just use it right here, right here. So let me do that this way. Let me take mx double dot to the other side. Say here's the transmitted force. The sum of these two equal to that minus mx double dot. And let's do that. When we do it, we get this expression. See, f naught cos omega t minus mx double dot. We know what x is, differentiate it twice, you get that. Okay? And it looks like we are in this situation, right? It looks like we're in this situation, something like that. And therefore, we're going to say that the maximum value of this function is the square root of f naught squared plus mx omega squared, just like I did it here. I had a cosine and a sine, and I said the maximum value of the square root of the square of that plus the square of that. So I have a cosine and a cosine and a cosine, okay? Cosine and a cosine, and I'm going to say square root of f naught squared plus mx omega squared, just like that. That's wrong. Because what we did up here is okay as long as the angles, these angles are the same, omega t minus theta. Here, the angles are not the same. One of them is omega t minus theta, the other one is omega t. Because of this phase shift, we cannot do that, okay? So, if we go that route, we can't use this, I don't want to say trick, but this observation, okay? You just have to plot this and find out what the maximum value is, or find it some other way. Okay. So, good. Let's go to our next problem. We have a single degree of freedom system. There is a harmonic load applied here, but this is not a force, it's harmonic moment. Okay, you're given information about the stiffness of that spring and this spring and the damping coefficient, and we are asked the following question. Find the maximum m naught. By the way, this omega, we are told what it is. This omega, we are told that is 400 RPM. We know omega. It says find the maximum m naught. We know what m naught is, so that the angle of oscillation is less than 15 degrees. In other words, the amplitude of oscillation, we want it to be 15 degrees. Now, at the end of the day, you've got to get the mother of all equation for this problem. This is a single degree of freedom system. And I'm going to give it to you right there. And this is obtained by drawing the free body diagram, taking the moment about for example, the point A to get rid of the reaction force. You should be able to do that. Do not be surprised if you get a problem like that on the midterm, because we have done many problems like that. It all hinges on free body diagram. We have done many problems like that, taking the moments about A, cleaning it up. I'll leave it to you to go through it to get the mother of all equations, but you are responsible for things of this type. All right, so if that is the case, let me go back here. We have, this is our M, so we call it M effective. This is our C, we call it C effective. And this is our K, K effective. And this is the same as F naught. And everything is the same. So we can use all the formulas that we got, except that we have to use M effective, C effective, K effective. All right? There we are. And that formula we have. Please go ahead. You see that in the when we did it in terms of X and F and things of that type. Okay? And just plug in the values. M effective is this. And of course, omega n is going to be, just plug in these values. This was all given to you. And there we are. This is the natural frequency. We are told that omega, the driving frequency, is 400 RPM. So just turn it into rad per second. And the frequency ratio is going to be omega over omega n. So the ratio of this over that. We have C effective, by the way. Okay, you find the damping coefficient, 0.15. So it's an underdamped system. And we go back to this equation. We want theta, amplitude of the oscillation, to be 15 degrees. Everything else on the right hand side is known except for m naught. So we're going to get m naught. And that solves this problem. Okay. Okay. Our next problem is coming out of Miriam and Craig's dynamics book. It's a nice one, so I want to go through it with you. Suppose we have a mass, 10 kilogram mass, and it is uh, maybe in it there is a motor that's turning and it has an unbalanced mass, and the the speed of that motor that's turning inside of it can be changed. Incidentally, if you take your cell phone, for example, and you know that you can put it on vibration mode, what is in it, in a sense, it's an unbalanced mass that is turning. Although the mechanism of it may have been different, but in principle, it could have been a motor sitting there which was turning at the speed which has an unbalance. The motor has an unbalance and make the phone to vibrate back and forth. Now, of course, these days things are done electronically. So I'm not suggesting that there's a motor in there, but in the old days, the only way you could make things vibrate pretty much was to have an unbalanced force. The easiest way was to do it with a motor. Okay, but anyway, let's move on. So inside of this, think about it. There's a motor which has an unbalance and makes it vibrate back and forth as a harmonic oscillator. Now, uh, the spring stiffness is given to you, 1080 Newton per meter. The C is not given to you directly, but a statement is made that allows you to calculate that. It says, look, the damper whose piston is resisted by a force, so this is the force of the damper when moving at the speed of 0.5 meter per second. So let's think about it. What is the force of the damper? It's C x dot. So we know the force, we know the x dot, the velocity. Out of that we can get the C. So it's a kind of a tricky way of telling you what C is. But anyway, let's go ahead. It says fine. First of all, find the damping ratio. That's not a big deal. And then it says plot that magnification factor, big M. Remember, I told you that some books call that expression 1 over square root of 1 minus r squared plus 2 zeta r squared. They call it magnification factor. I'll come back here, but I want to show you what I'm talking about. This is called magnification factor. And they want us to plot this for different values of the frequency ratios and say a few things about it. And that's what I'm going to do. All right. And it says, okay, look at your graph and find the maximum value of M. Fine, that's no problem. When we plot it, we can find we can answer this piece. Now let's see now. Mass is given, stiffness is given in the statement of the problem. In a weird way, it says if the force is 30, velocity is 0.5, what is the value of C? Okay, that's easy. First of all, this will give you the natural frequency, and by saying that force 30 is equal to C times x dot, you can get the value of C, and the value of C is 60. And damping ratio is C over C critical. You put the stuff in here and you get your zeta. Now let's go to the other page. It says, okay, you know zeta, plot that function. Magnification factor, dynamic magnification factor. The only thing is that it says for a certain range of R going from, or the speed going from 0 to 300 RPM. So basically R going from 0 to 5. Okay, no problem. I can take this, use a package, plot it between 0 and 5. And this is the same thing except that the scale I've done it from 0 to 2 so you can see this peak better. Now, let me remind you what the significance of this M is, if you apply a dynamic force to that mass, which may be coming from that unbalance, harmonic force coming from the unbalance. And if you know what the amplitude of that force is, of that dynamic harmonic load is, if you want to know how much the mass moves, okay, take that F naught, amplitude of the force, divided by K, this is a static one, multiplied by M. So you can see that F naught over K, static deflection, is actually magnified by almost 1.7 times. So it is not just taking that force, dividing it by K to find out how much the mass moves. It's multiplied by 1.7 coming from magnification factor, or 1.8. And it happens at this point, R equal to 913, which tells you you can actually find what the speed of the motor is. So when the motor runs at that speed, which means omega n times that, you get 1.7 or almost 1.9 times the static deflection. Don't confuse this thing with moment, please. This is the magnification factor. All right. We'll do another problem from Craig, Miriam Craig. So we have the whole shebang here. A mass, there is a force oscillating, harmonic force, which make it oscillate at that frequency and that amplitude. We have a spring, we have a damper. It says, hey, you know what? Plot everything. Plot everything. Okay, first thing we're going to do, I want to point out to you that here initial conditions are given. So when I say get the whole shebang, means that write the whole response based on the initial conditions and the information that's given in the first 2 seconds. Okay, first thing that we need to do is to find the mass. So you take 50 pounds divided by 32.2, that's going to be that many slugs. Not slinge, slugs. Okay, then natural frequency. Well, we have a K, we have the M, we find the natural frequency rad per second. Then the damping ratio. We have the C is drawn here for you, 18, and C critical is just either 2m omega n or 2 square root of km. There we are, okay? Frequency ratio, omega over omega n, that number, okay? And when we have R and zeta, we can go and find the amplification factor, okay? Your big M. And why do we need this big M? Because it gives us big X. Big X is simply F naught, big F naught, 160, divided by K times this M. Okay, let's move on, right there. So we get this number, these are all in feet. So we go here, we need the damping frequency, because we are considering not only the steady state response, we also want to do the transient response. So that happens with omega d, that dies down with the frequency omega d. Okay, remember that we have transient plus steady state. The steady state is not a big deal. We need big X cosine of omega t minus theta. Of course, I need theta. I have to get it, and I will. And this term has exponential with a negative sign, and there is zeta omega nt on the top, and there is, sine of omega d minus its own shift, or plus its own shift. The way it's done in Inman, they use plus. Okay, no problem. This one is minus, this one is plus. Okay? You can write it like that, or you can write it like that. Entirely up to you. Please go back to the stuff that we did last week. Either like this or like that. Actually, it wasn't last week, it was Tuesday. And there was a review of it this morning too. So this is our slides 6 and 7. Okay, to find x, to find a and phi, or c1 and c2, whatever you like. I will use the first approach right here because we had gigantic formulas for a and phi. First, you need to find theta. I do need theta, of course. I plug in, zeta was found, r was found, 2.9, and this is the gigantic formula that I'm talking about. We have x, big X, we have theta, we have x naught, and we have v naught. Just literally crank it out. And you're going to get this and that. So here's the whole shebang. You know everything. This is your A. This is your zeta omega n t with a minus sign. There is your omega d. There is your phi. There is your big X. There is the driving frequency, 60. And this is the theta. And you plot. Okay. This initially happens because of the transient response that's dying down. And then after that, this survives. This dies down, this survives. And you can see that it's a cosine of that frequency, 60, not hertz, 60 radians per second. All right, folks, so that takes care of the lecture today. I told you, I cautioned you that there isn't a lot of math there, but this is something that you have to know, meaning at least you should have written it down so that you can use it, okay? And the fundamentals you have to be able to derive too. I gave you an example of that, the bar that was rotating, and I said that here is the equation, the mother of all equation, which involves rotation of the bar, but you should be able to get it. All right, good luck. So we're going to have a quiz on Tuesday, and it is covered through today's lecture. Next Tuesday, we're going to have a quiz, a 30-minute quiz toward the end of the lab, and it is 10 multiple choice questions, but it will cover through the lecture today. Good luck and have a good weekend.